I have here a conducting wire, a square. I could have chosen any other shape. Try to make you see three-dimensionally. And I approach this conducting wire with a bar magnet. The bar magnet has a magnetic field running like so. As I approach that loop, that conducting wire, moving the bar magnet, that's essential. I can't hold it still, I have to move it. If I come down from above and I move it down, you're going to see a current going through this loop. And that current will go into such a direction that it opposes the change of the magnetic field. The magnetic field is in down direction and it is increasing as I move the bar magnet in. Then this current loop will produce a magnetic field which is in this direction. And when you look from below, the current will go clockwise, producing a magnetic field in this direction. If you move the bar magnet out, then the magnetic field is going down here, then the current will reverse. The current wants to oppose the change in the magnetic field. And that's called Lenz Law. It is the most human law in physics, because there's inertia in all of us. We all fight change at some level. Lenz's law is extremely powerful in always determining in which direction these induced currents will run. It is not a quantitative law. You cannot calculate how strong the current will be. But it's very useful, as you will see today, to know the direction of that current. That gets you out of all kinds of problems with minus signs. I now want to do a demonstration which is very much like what you see here. I have here a loop. That is the square that you see there, except that it's not one loop, but it is many of them. Hundreds, doesn't matter. And what we're going to show you is an ammeter that is connected. So there's somewhere in this circuit an ammeter. I have a bar magnet, and I'm going to approach this conducting loop with the bar magnet. And you're going to see a current running in one direction, and when I pull it out, it will be running in the opposite direction. And when I hold my hand still, so that the magnetic field is not changing, no current. You're going to see the current meter there. And here is my bar magnet. I come close to this conducting loop. Notice, you see a current. I pull back, current is in the other direction. Now I will go faster, so that the change of the magnetic field per unit time is stronger. More current. I go out fast. More current. So you see, it's the change of the magnetic field that matters. If I come in very slowly, which I do now, very slowly, you almost see nothing. And right now, the entire magnetic field is inside this loop. The strongest I can have it. Nothing happens because there is no change in the magnetic field. It's only when I do this that you see the current. So an induced current is clearly the result of a driving force. There must be, just like we had with batteries in the past, there must be an EMF. There must be an electric field that is produced in this conducting loop. And so I create now an induced EMF. We used that word EMF earlier for batteries. So now we have an induced EMF, which is the result of this changing magnetic field. And that, therefore, is the induced current times the resistance of that entire closed conductor, whatever is in there. In this case, the total resistance of all these windings, of all the copper wire. That's Ohm's law. So the induced EMF is always the induced current times the resistance. Faraday did a lot of experiments. And one of the experiments that he did was that he produced a magnetic field. So he ran a current through a loop of some kind. Let's say he ran a current going around, creating therefore a magnetic field. And he was switching the current in and out so that he could change the current. And so it produces a magnetic field. And this magnetic field changes when you close and open the switch. And then here, he had his second conducting wire, just like we had there, and he measured in there the current. And what he found experimentally is that the EMF that is generated in here, which I will call EMF generated in my conducting loop number 2, is proportional to the magnetic field change produced by number 1. So the field goes through number 2, and this field is changing. So he noticed that if the change is faster, as you just saw, you get a higher EMF. He also noticed that E2 is proportional to this area, so to the area of number 2. And that gave him the idea that the EMF really is the result of the change of the magnetic flux through this surface of number 2. And I want to refresh your memory on the idea of magnetic flux. We do know, or we remember what electric flux is. And magnetic flux is very similar. If this is a surface, and the local vector perpendicular to the surface is like so, of course it could be in a different direction, and the local magnetic field is, for instance, like so, then the magnetic flux through this surface is defined, we call it phi of B, is the integral over an open surface. This is an open surface of B dot dA. An electric field, we defined in exactly the same way, electric flux, except we had an E here. There was nothing there. So if this magnetic flux is changing, Faraday concluded that then you have an EMF in this conducting wire.